This is the third video of the 4-video set that make up the ECOFusion webinar. This video will be dedicated to a study of the electron beam physics. We'll start with a look at the electron beam parameters, and then go on to take a look at the electron beam's interaction with the solenoidal guide field, the background gas, the ion beams, the electron interaction with itself, and the interaction with trapped ions that are in the system. We assume an electron beam current of 10,000 amperes so that the electron beam current is equal to the ion beam currents described above. With a typical cathode emission of 10 amps per square centimeter, this implies a cathode radius of about 18 centimeters. Typically, thermionic emitting cathodes have temperatures of about 1/10 of an eV, and this leads to an electron beam emittance of about 200 pi millimeter milliradian, and an electron beam momentum spreads of 7.4 times 10 to the minus 4 for the deuterium case, and 1.6 times 10 to the minus 3 for the tritium case. Here we see a depiction of the electron cooler. Electrons will leave the hot thermionic emitting cathode and be accelerated by electrodes present in the electron gun. Solenoidal guide fields, created by wire windings, will then guide the electrons till they are nearly merged with the ion beam. The merging is completed by a toroidal magnet system that has slightly curved magnetic field lines that guide the electrons into complete overlap with the ion beam. The ion and electron beams then coast along together, with the ion beams losing their momentum errors to the electrons in the cooling process. Once the cooling is done, the electrons enter a downstream toroid, which gently bends the electrons out of the ion beam, and then enters two solenoidal magnet systems that take the beam up to where they are efficiently collected in a collection plate. The first interaction to study of the electron beam is the interaction that the electron beam has with the solenoidal guide field. The electron optics become trivial, as the electron optics follow the solenoidal and toroidal guide fields that are present in the system. It's been calculated that a 100 Gauss solenoidal field in the cooler straight section is sufficient to accomplish this task. The electron gyro radius in these solenoidal fields is about 107 microns for both the tritium and deuterium cases. The gyro radius motion reduces the solenoidal guide field by about 3/1000ths of a Gauss, leading to a plasma beta of less than 10 to the minus 4, indicating that from a plasma sense, the electron beam is an extremely stable plasma and should not have any problems with instabilities along its path. Electron beam neutralization by background ions is a very important topic with regards to the ECOFusion system. The electron beam energy is only 30 electron volts in the tritium cooling case, and yet the electron cooling current is specified as 10,000 amperes, and therefore we need a very high level of neutralization of the space charge in order to maintain those parameters. It's important to note that background gas ions within the vacuum system will form at about 1/40th of an electron volt of energy, and that a 1/40th of an electron volt ion will be trapped in any potential greater than 1/40th of a volt. Therefore, the ions should neutralize the electron space charge to a considerably smaller value of voltage than the 30 electron volt energy of the beam. The electron cooling sweeping time has been calculated to be 27,000 turns if the ions were swept out of the electron beam consistently. But what will happen is the ions will bounce along from one end of the cooler to the other, and so therefore it will take quite a bit longer for the ions to be swept out by the electron cooling force. As a result of these calculations, it is expected that the ions will significantly eliminate the electric self-space charge field of the electron beam. However, those ions that are trapped within the electron beam will serve as scattering centers for the electron beam. For the tritium case, 4.7% of the electrons will scatter at greater than 100 milliradians in 1 meter. For the deuterium case, the situation is much better, as only 0.7% of the electrons will scatter by that amount over a 1 meter distance. Multiple scattering is also important, and in the tritium case, one would see a 20% emittance growth in 10 centimeters, while as for the deuterium case, 7.3% emittance growth is expected within a 10 centimeter distance. These values will not represent a problem at 400 kilovolts, but the scaling is very strong, and at 100 kilovolts the problems are significant. It's this effect that has caused the design to be done at 400 kilovolts. Once the design was complete, which is a 6-month process, it was realized that 400 kilovolts might be higher than the optimum design energy. Therefore, some improvement in ECOFusion can be done by operating at a slightly lower energy. Since the electron cooler within ECOFusion requires such a high level of space charge neutralization, it is useful to once again do a sanity check and compare the design to working electron coolers of the past. Electron cooling collectors have worked well past the space charge limit in many, many instances. In those collectors, the ions are trapped longitudinally by electric fields that are set up within the collector, and the ions are trapped transversely by the containing magnetic fields. In Fermilab's electron cooler, as I recall, 22 amperes at about 500 volts was passed through their collector. In the bench test of my thesis experiment, we had a 4 ampere beam with a few hundred volts, and later we tested operation of the 3 million volt accelerator with 0 volts on the collector and no magnetic field. All of these experiments have shown the strong presence of neutralizing background ions in an electron beam. The ECOFusion experiment will need about the same current density as these experiments, but it does have somewhat lower energy than the beams in the previous electron collectors, and there is a much longer beam path for the electron beam to traverse. And note that what is required is that one has a reversed field near the electron gun in order to contain the ions longitudinally, and that technology has been covered under patent number 7501640. Now we'll look at the component designs needed for the ECOFusion system. We'll take a look at the dipole design, the quadrupole and solenoid designs, the electron beam components, and look at some power estimates required to drive those various components. The dipole design has been studied by the well-known program Poisson. The power requirement for the coils is about 15 kilowatts for the dipole designs for the ECOFusion system. An analysis has been done to take a look at the quality of the field throughout the dipole design, and even at the outside edges of the dipole, it has been determined that the fields will be adequate for ECOFusion functioning. A quadrupole has also been designed, and while this quadrupole could use some improvement due to its large size, it's perfectly acceptable to use such a quadrupole in the initial tests of the ECOFusion system. Solenoid designs have also been done with Poisson, and they fully meet the required specifications of the ECOFusion system. In all cases, dipole, quadrupole, and solenoid, the designs are well within standard state-of-the-art for making such components. The electron beam components are likewise well within the state-of-the-art. We use a standard cathode surface for emitting of the electrons. We use magnetic solenoid and toroids that have simple wire windings to yield the 100 Gauss fields required to guide the electrons along their path, and a collector that will suppress secondaries. The injection system is very simple, as one just takes and puts a small lip into the wire windings of the long solenoid, which will allow the injected beam to pass in through the solenoid and into the main electron cooling section. Here we have a presentation of the hardware power estimates of the various magnets used in the system. And what can be seen is that the quadrupole powers are all quite low and can be easily handled within the system, but the solenoid powers are too large for the given output power of about 50 kilowatts of the ECOFusion device. For this reason, permanent magnets are intended to be used for the solenoids, quadrupoles, and dipoles to reduce the input power to the ECOFusion system in order to make it viable by having more power out than is required to run the device. The solenoid and toroid powers will be necessary. However, the design here has specified a single turn of copper, and should it be desired to reduce these further, there is a trade-off by putting more copper windings in. One could reduce the power.